So thank you so much for inviting me here and giving me an opportunity to talk about this. It's a real honor. And yeah, wait, now something happened. Okay, I can see my slides again. Right, so probably not a surprise, I should start with a little disclaimer that this is not a maths talk. So I won't prove a new theorem or something. It will be a talk about maths, which is basically the theme of this, this symposium. And so sort of a very, very rough overview of what I want to talk about is that I want to claim that formalization of math encourages or even enforces abstraction boundaries. I'll talk about what I exactly mean with abstraction boundaries, and that complex projects in maths can benefit from this. Maybe also as part of this disclaimer, I'm not a philosopher, and I can very much identify with what Akshay said about being a termite in the mound, and I'm now trying to sort of make some claims about global structure or try to look at it from the outside. But bear with me if I say something stupid. So Akshay wrote this essay, which I found extremely interesting, and I will try to briefly recap it, or at least how I perceived it. So the essay was titled "Some Thoughts on Automation and Mathematical Research." And the central question with which Akshay opens the essay is, in the past decade, we've seen some massive changes in what technology has done in our society. For example, AlphaZero completely changed chess overnight. And I think, so this was a product by DeepMind. They also have AlphaFold, which has massive implications for protein folding and transitively for medicine and things like that. And the question that Akshay asks is, what impact would a sort of analogous AlphaZero have on mathematics? And I think his main claim is that mechanization of mathematics, or mechanization of our cognitive processes, will enhance our mathematical abilities and alter our understanding of what mathematics is, maybe even to such an extent that we barely recognize it even. So then he goes on to describe a Bayesian model of the social fabric in the mathematical community. And he observes that the level of consensus that mathematicians have about what mathematics is, what beautiful mathematics is, what hard mathematics is, what important mathematics is, and which mathematicians are working on the important problems, or which mathematicians have a really good sense of taste and things like that. This level of consensus that we have about this is much higher than in neighboring fields of research. And the hypothesis is that we mostly agree on the validity of proofs, and this has a stabilizing effect in the Bayesian network of values that we attach to things. Okay. And if AlphaZero arrives on the stage, then this will thoroughly shift this value network. It will overturn our ideas of what is beautiful, what is hard, what is important in mathematics, and as a corollary also the human beings doing the mathematics, how we value them, who has great skill, who has great taste, etc. Okay, so my plan for this talk. Right now, AlphaZero does not exist, but some forms of mechanization do exist. And are we already seeing some effects? That's sort of what I want to think about with you. And I'll argue that there are benefits, and I'll motivate these claims by looking at some things that have happened in the Lean community. I'll talk a bit about Lean in a moment. And in particular, I'll take examples from the liquid tensor experiment, which is a project that I've been leading in the past 2 years. So this is sort of the table of contents. Here's where we are. I want to talk a little bit about what lean is, what the liquid tensor experiment is, and what I mean with abstraction boundaries, which I already mentioned a moment ago. And then I want to look at how formalization and these abstraction boundaries interact with each other, with sort of looking at small scales of mathematical activity maybe. I tried to order this, I tried to organize my thoughts, and I don't think this is the final way to think about this, but yeah, I've tried to put it in some sort of order. So first of all, I want to look at like sort of the smallest building block in mathematics, which is lemma statements, and how using abstraction boundaries there can reduce cognitive load. Then I want to look at definitions, specifications, which is a word that I chose to capture definitions plus some important theorems about them. Then about like going much bigger, look at large projects, and then finally about how you communicate results of a project with the mathematical community at large. And then finally, I want to draw a conclusion and see how this ties back to Aleph 0. Okay. And so these benefits that I'll talk about are what I mainly experienced myself while working on the liquid tensor experiment, but I really don't want to claim that these are the only benefits. I'm convinced there are many others. And if you're interested in those, I can very warmly recommend an essay by Patrick Massot called Why Formalize Mathematics. I think there are a lot of important points there that I will not be able to talk about today. So what is lean? Lean is a piece of software developed by Leonardo de Moura and by now a larger team at Microsoft Research. And it's a free and open source programming language, which I first found very interesting that Microsoft would develop free and open source software. But yeah, change happens. And yeah, so what makes Lean special is that it's a programming language that has dedicated support for definitions, theorems, and proofs, which makes it a tool that we can use in pure mathematics to work on proofs and things like that. And this special support is a result of Lean's type system. I will not go into the technical details of what a type system is, but it's something that computer scientists have been using for a long time to structure their programming efforts. And it's a very powerful system that can be used as a different foundation of mathematics. And so Lean's type theory plus 3 standard axioms are equiconsistent with Z of C plus a countable hierarchy of Grothendieck universes. And this equiconsistency proof is, of course, something that lives outside of Lean. But people have proved this on pen and paper. That you can build a model of Z of C plus countably many Grothendieck universes inside Lean, but you can also build a model of Lean's type theory inside Z of C. And so you can sort of transport results from one to the other. I think Jeremy is the best person here. Let me give you the mic, then you can quickly comment on this.
So Leo's initial intent was to develop a system that could be used for formalizing mathematics and also verifying hardware and software.
Yep. So there is this type system, which is, I would say, the bare metal of Lean. And sort of like, you can think a bit about it as an assembly language for some processor. And then on top of this, a very powerful feature of Lean is the so-called tactic framework, which is a user extendable framework which provides a very flexible and powerful way of writing little tiny programs in Lean that will generate proofs for you. So you don't have to write proofs all the way at the lowest level of mathematics, stringing axioms together, but you can try to generate proofs. You can try to write Lean programs that will generate proofs for you. And so you can start working at a higher level. So I think maybe it's best if I just give you a practical demonstration of how this works so that we sort of have all seen what lean is. Sure.
Is a tactic in the type system itself? So there's a type of tactic?
Yep.
Wow.
Sort of, yep. It's a piece of software.
Little programs that run it.
So what I want to do, I've opened some editor that has special support for lean. And there are two lines that you can basically ignore. One of them is importing some stuff from a library. In particular, it's importing the definition of prime numbers. And then this third line is enabling some notation for factorials. And what I want to do is prove with you, or reprove with you, a theorem that might have won a Fields Medal several thousand years ago. So, for all natural numbers n, there exists a p greater than n, such that p is prime. Okay, so this is the statement, which hopefully is fairly readable to all of you. And now, just like in LaTeX, you would write begin and end. And then between the begin and end, you have to write a proof. Except that, well, this is now a bit hard. We have no idea what to do, but we can use Lean's superpower and open an extra window. And let me see, is this, I think, yeah, the font size is okay, right? Or should I increase the font size? Okay, good. And so now, Lean is showing us on the right-hand side what it has understood so far. And so it says there is one goal: you want to prove that for all n, there exists a p, etc. And so I'm going to give it an instruction. I'm going to say, well, assume n. And now that it changed a little bit, it says in yellow, okay, now you have an assumption, as an assumption, you have a natural number n floating around, and you want to prove that there exists a p for this particular n. I could have used a different name. I could have said, assume k, and then we would have a k floating around, and instead of n over here, it would have said, it now says k. Okay, so yeah, that's type theory for you. So if you look over here, it says for all n natural numbers. So because in the goal it knows that you have to prove something for all natural numbers. If you say assume k, then it knows, well, you have to prove something for all natural numbers, so k must be a natural number.
But if there were two all, if there were alls, then it wouldn't know which one.
It would take the first one. Yeah. Okay. So now we introduce some new notation. So we say let capital N be n factorial plus 1, and let p be the minimal factor of capital N. So you see that some more orange or yellow stuff appears in our goal state on the right. And now we claim that this p is going to be a prime number that is larger than n, so it should do the job. So we say use p. And you can see if I put the cursor at the beginning of the line, you see the old goal, that there exists a p with some properties. And after we instructed it to use the p that we just defined, it says, okay, now what's left is that for this particular p, you have to tell me why is p larger than n, and why is p prime. And because I prepared a little bit, I know that it's useful to first prove that p is prime, and you can use that later on to prove that p is larger than n. So I'll make a claim. I'll say p is prime and add a comma. And now something happened. Now there are two goals. So what have did is it introduced a new sub-goal. It says, starting from what we know so far, I'm going to prove that P is prime. And then in the second goal, this assumption that P is prime is floating around in my context, and I can use it to prove the original goal. And you can see that it automatically generated a sort of LaTeX label for this assumption that P is prime, and it called it this because I didn't give it a name. So, but let's say that it's like the most fundamental hypothesis about about P that we can have, so we call it HP, and now it uses the name HP. Okay, that's just a little bit of management, like you would write LaTeX labels to refer to things later. Okay, so now I'm just going to prove this using sorry, and once I did that, Lean says, goals accomplished. You've proved that P is prime. Now you can use that later on. And I'm going to say, well, I'm also going to make the claim that P is larger than N. So now I again have two goals, one that P is larger than N, and finally the original goal. I'm also going to prove that using sorry. I'll answer it in a moment. And then now we should be able to finish the proof because we have two assumptions, namely that P is prime and that P is larger than N, and we should be able to combine those two to finish this proof. And we just tell Lean, well, this is exactly the combination of the assumptions HPN and HP. And so Lean agrees and says, yes, goals accomplished, you're done. Except that if we look at line 5, there is this orange squiggly line under the word theorem, and if we hover over it, it says, declaration Euclid uses sorry. So Lean is not forgetting that we use sorry and says, no, this is cheating. I mean, I understand that this is the global structure of the proof, but I'm not letting you get away with this word sorry. So sorry is a tactic that basically just says you can prove anything, but you have to assume that you have a proof of false. So it's of course, sorry is inconsistent with, or sorry makes Lean inconsistent. So you have to make sure that you don't use it, and Lean keeps track of where you use it. So I don't think I'll finish the entire proof because it's not the main topic of the talk, but let me show a little bit about how you would go about this. So let's prove that P is prime. And I'll just ask Lean for a suggestion about what we could maybe do. And so suggest is a tactic. So it's a little program that looks at the entire library and just looks which lemmas might be useful to make progress here. And it gives me an entire list. It says, well, you could use things like the definition of a prime number, maybe a slight variant on the definition. And then this fourth suggestion says min fac prime, which sounds like a lemma that might prove that the minimal factor of a number is a prime number. So let's click on that, and that Lean helpfully copies it to the left-hand side. And now our goal has changed, but we're not done yet because we still have to prove something. We have to prove that capital N is not equal to 1 because the minimal factor of 1 is not prime. Okay, so now we need to show that capital N is not equal to 1. And why is that? Well, capital N is defined as little n factorial plus 1, and factorials are positive. So if you add 1, then the result cannot be equal to 1. So we say, well, observe that n factorial is positive. And again, observe is a little tactic that looks through the library for a way to prove this result in one step. So basically it will look for a lemma in the library that says factorials are positive. And it found one. So you might have seen a yellow bar over here, which meant that Lean was searching for this proof. And now we can say, okay, we now have this assumption that n factorial is positive, and now we should be able to just finish this with a little bit of juggling around with inequalities, and there's a tactic for that. It's called linearith. So we invoke linearith and that should finish the job. And you can see the orange bars, which means that Lean is thinking and thinking and trying to find the proof that it just found a moment ago. And this shows how stupid Lean is. It just forgot the proof it found 5 seconds ago and starts the search all over again. So to speed that up a little bit, we can add a question mark, and that will instruct Lean to print the proof on the right-hand side, and then we can just copy it so that it doesn't have to search for it over and over again. So now if we click this, now our proof is pretty nice and fast again. Okay, I'll not prove that P is larger than N. I can do this if you're interested in one of the breaks, but I think this, you get the main idea of how this works. Okay, so that's what I wanted to say about Lean. So now what is the liquid tensor experiment? So on December 5 in 2020, and okay, so I'm from the Netherlands, and December 5 in the Netherlands is Sinterklaas, or like Saint Nicolaas. So it's a day on which everybody gives each other presents. And so when Peter Schulze posted this online, I interpreted that as a present for me on Sinterklaas 2020. He posted a challenge pretty much directed at anyone interested in computers and mathematics, saying, check the main theorem of liquid vector spaces on a computer. Okay, so now I no longer really need to explain what he meant. He basically meant take a system like Lean. There are also other alternatives. Take this theorem of liquid vector spaces and enter it into Lean or one of these other systems. And so what is the theorem? It's a theorem that he worked on together with Dustin Clausen. And I'm not going to go into any details, but in the end, you have to show that certain X groups in the category of condensed abelian groups vanish. And yeah, this is all pretty brand new mathematics and uses a lot of pretty advanced machinery. So, and the reason he asked for this challenge was that he had worked on this proof for an entire year, basically. And he says himself that he almost went crazy over it. And in the end, he wrote something down on paper, but he wasn't happy with it because he didn't understand the global picture. He didn't really understand the proof. And he felt like 99.9% sure that it was right, but it's of fundamental importance in this new field of liquid mathematics. And so he wanted a higher degree of confidence. And in addition, when he asked around for people who had been organizing reading groups on this material, he asked, like, did you actually also go through the proof of this theorem? Everybody told him, no, we skipped that because it looked really intimidating. Okay, so now finally, as the last part of the introduction, what do I mean with abstraction boundaries? So this is a pretty old concept from software development. In some sense, I don't think I'm going to tell you a lot of new things in this talk, but basically we've been putting together ideas from, well, software development, mathematics, and yeah, just using them in new ways. So it's an old concept from software development. And if you're familiar with languages like C and C++, you can think of the header files that are over there. So the main theme with these abstraction boundaries is you try to get a grip on complexity in whatever you're doing by fencing off implementation details and only providing a certain interface through which you can interact with whatever you're doing. And formalization provides a way to take this very serious on many different levels when you're doing mathematics. So let's look at some examples. First of all, I want to look at lemma statements. And this is sort of abstraction at the lowest level. And in Lean, we have a name for this. It's called proof irrelevance. It says, whenever you have a lemma statement, if you have any two proofs of this given lemma, those two proofs are equal. So we don't care. Under the hood, when you're working on this lemma, trying to understand it, trying to prove it, you care about the proof. But once you're done, you sort of seal it off and you say, okay, now I can just use this lemma And I can use it no matter how it was proven. I can use it in the same way. And so a lemma statement is in some sense a very tiny abstraction boundary in itself. And this sounds like a very innocuous remark, but I think actually that this was the most helpful thing. That's also why I say it, why I claim it has been reducing cognitive load, because when you're working on an extremely complex mathematics project on a very complex proof, and certainly this proof that Schultz had written down is an example of that, there's a lot of raw proof complexity that you just have to deal with. But there's a lot of cognitive load also arising in mathematics by the fact that you need to keep track of lots of different things. So you might need to keep track of discrepancies between statements and proofs. You might be referring to a paper written 10 years ago by someone with a really nice lemma statement, and then a proof, and you realize, well, actually the proof proves something stronger than what the lemma statement says. And I want to use the stronger thing. So instead of saying by lemma 3.5 from that and that paper, you say by the proof of lemma 3.5 of that and that paper. This is extremely common practice in mathematics. In some sense, there's nothing wrong with it, because, I mean, the proof does in fact prove the stronger statement. But it does mean that as a reader of this proof, you have to go back to the proof of 3.5 and not just check the statement, but you have to read the proof again and see, do I agree that it proves something stronger? And this adds cognitive load to what you need to do. You might have written lemma 3.5 yourself in the same paper, and you're working on section 7 right now, and then you feel obliged, well, okay, maybe it's bad practice to say by the proof of lemma 3.5 in a paper that I'm just writing myself. Let me go back and actually fix that lemma and improve the lemma statement. And maybe you were actually doing something even slightly more evil. You were saying, by the proof of lemma 3.5, under the additional assumption that we see that the following stronger statement holds. So then you need to tweak this lemma. You go back, you tweak the lemma, and you have to add this additional assumption, which is harmless because it's satisfied in all the other places where you wanted to use lemma 3.5, except you have to check that it's actually satisfied. And on paper, maybe you don't bother, but it's maybe also, it would be honest to do that. Then you need to keep track of side conditions to lemmas. Like when you're applying a lemma, there are one or two conditions that are really essential. That's where the real content of the lemma is, and then there are maybe one or two. Like maybe you need to check that capital N is not equal to 1 whenever you want to use that the minimal factor is prime. And of course you just ignore this, because who would have used the minimal factor of a number if the number was 1? You wouldn't have even mentioned it. So usually you can get away with skipping this keeping track of side conditions. But if you don't understand the proof, and if the proof is very complex, then you think, well, maybe the devil is in the details, and I do want to keep track of all the side conditions, and this adds a lot of cognitive load. And finally, maybe they're just unstated assumptions. Maybe there's just this lemma there, and if you're lucky, the author wrote in the introduction of the paper, yeah, in this paper, K is a field of characteristic 0, and then in lemma 3.5, there's only the statement, let K be a field, and it's implicit that, of course, it must be a field of characteristic 0. And so you have to keep track of this, and it might mean reading more than just the proof of lemma 3.5, and maybe even more than all of section 3. Maybe there are unstated assumptions that are just part of the community and are not even mentioned in the paper itself. Okay. So formal maths does not decrease raw proof complexity. It's just inherent to the problem. We're not getting rid of that. But I claim that it certainly takes care of keeping track of all these other sources of cognitive load and takes that burden off the human. Yeah. So the result is that most of your mental RAM can be spent on trying to understand the global picture, the big picture. And while you're working on a lemma, you focus on the proof complexity of that lemma. And You can spend all your mental capacities on that, but once you're done, you seal it off, and your focus returns to the big picture, and you don't have to worry, like, oh, I need to keep in mind that I had this unstated assumption floating around, because it must be explicitly present in the lemma statement. Otherwise, the formal proof checker will not accept what you've done. So what was our experience working on the liquid tensor experiment? Well, Schulze himself wrote, when he was, so he wrote a second blog post when we were done with the key ingredient of his proof, and he was reflecting on the process. He said, one key problem I had when I was trying to find this proof was that I was essentially unable to keep all the objects in my RAM. And I think the same problem occurs when trying to read the proof. And I very much agree with that, because I was sort of leading a team of between 5 and 15 people, changed over time, trying to work on this project. And well, I needed to sort of say in which direction we were going. So I tried to understand what is the global picture of the proof. So I would sit down with a stack of paper and a pencil and try to figure out, okay, how do things fit together? Where should we be going next? And I tried this 2 or 3 times and it just didn't work. It failed. So Lean really was a proof assistant. These interactive theorem provers, this formalization software, is sometimes called a proof assistant, and most of the time that's just preposterous, because all it is being extremely pedantic. It's not assisting at all. But in this case, I'm convinced Lean really was a proof assistant, because when I didn't understand the global picture, I would say, okay, but I do understand that we will need this lemma, and I have no idea how it's proven, but I do understand the first 2 lines of the proof. So let's just write down the lemma statement and write down the first 2 lines of the proof. And I had this experience that maybe you took Latin in high school, where you're like, okay, another foreign language, where you're like, you get this text for homework and you need to translate it. And you think, okay, well, I learned all these words, so let me just read through it and see what it's about. And halfway through the page, you realize I'm completely lost. I have no idea what the text is about. So you sit down with your dictionary, you translate the first 2 lines, and you say, aha, okay, now I see what the next 2 lines mean. I don't know if you've had this experience. I've had it a lot of times in high school, and I had a similar experience here, where I would work through the first 2 lines of the proof and then realize, okay, now I see which ingredients that weren't written down on the page, but were implicitly used, how they fit together for the next 2 lines. And actually, when the project came to an end, things really started to click together, and I could understand the global picture. It still took a long time. I understood the global structure, but it was far from the case that I would be able to reproduce the proof without Lean. Like, if you would give me 3 days to write down the proof from memory, I wouldn't be able to do that. But now it's getting to a point where I do think the full proof fits in my RAM, because I understand it on such a high level that I can just reproduce all the components. But getting to this point, I continuously checked back in Lean, because when I tried to simplify a certain statement, I was like, okay, but maybe I'm simplifying it too much and this doesn't actually work. Let's go back to Lean, let's check if this should work. And this is only a very recent thing where I feel confident that I can say, okay, I can understand the proof without Lean. But Lean really was a tool that, in my opinion, was essential to getting me there. So now that was about lemma statements and about reducing cognitive load. So now I want to sort of go one step higher in this sort of scale of like tiny little components of mathematics to big theories and collaborations, etc. And so I think definitions are one level higher. And they abstract the properties of a concept. And I think that it's there is this sense, and Grothendieck was a champion of this, saying definitions are not just they don't just exist. There is a sense of having a good definition or a bad definition. A definition can be just right, or a definition could need some improvement. And Grothendieck actually he wanted to prove the wave conjectures, but he wanted to prove it using the right technology, using the right definitions. And he wanted to wait till the right definitions fell in place and people had discovered what needed to be done. History took a different course, but a lot of the time this strategy paid off for Grothendieck. And so the sense that we have is, I mean, think of group theory maybe. There was a time when we didn't have the definition of a group as we know it nowadays. And basically people always had some collection of matrices in mind, or like a representation of the group. But once we had the definition of a group, it was an abstraction that allowed us to develop this whole theory that we now call group theory in an effective and efficient way, I would say. So with the right definitions at the right level of abstraction, with the right properties and axioms for these objects, proofs will often write themselves. That's a sense that we have. And vice versa, this means that if you have the wrong definitions, these definitions will make you suffer, and it will be harder to write the proofs. And formalization of mathematics amplifies the suffering. So there's a strong incentive to not just dive in. Whoa, I'm too enthusiastic, sorry. Not just dive in and start doing things, but take a step back, take a moment to think, what do we actually want to do? What is the right definition? And this is an example. I think this is a wonderful example. It didn't show up in the liquid tensor experiment, but it's an example that's well known in the formalization community, namely that of limits and filters. So when you start doing calculus, first, second year calculus, you have the notion of a limit, but then there are lots of different variants. You can take the limit of a function f while x approaches some point x0, and you don't really specify how the point can approach x0 from anywhere. But maybe you want to consider a variant where x approaches x0 from below. Or maybe you don't actually want to approach a point, but you want to approach infinity. And so I just wrote down 3 variants, but there are easily 10 different variants. Maybe you want to take the limit of a sequence instead of the limit of a function. Maybe you want to take the limit while only considering rational values of x. Maybe you want to take the limit, but x is not allowed to actually take the value x0. You want to exclude that. And then there is this fundamental lemma that limits compose. So somehow, if you know the limit of f at point x, and then you want to take the limit of g at the point fx, then this composes. But that would easily be 100 lemmas because you have to take care of all these different variants. And all of them come with basically the same 10-line epsilon delta proof. So this seems very impractical, and it is. And so Bourbaki already came up with the idea of using filters to work with limits. But they didn't actually really push that idea as far as maybe they should have. And so filters are used all over the place in formalization of calculus. And actually, it unifies all these concepts. And not only that, the proof, instead of juggling around epsilon and deltas, becomes a very conceptual 3-line proof that is a really easy computation. So this is sort of one way where formalization pushed people into an abstraction that then simplified a lot of proofs. So next I want to talk about specifications, which is my one-word abbreviation for sort of a definition of a concept together with like the main properties, the main lemmas that you should know about this object. And the idea is roughly that while creating a new definition, you write down its main desired properties, and these properties form the specification, form the spec. This is also, again, a concept that is quite well known in software development. And the result is that if you write down these specs without fleshing out the full theory of the object, it's a lot easier to refactor the spec if you realize, okay, I actually needed a slight variant. I needed one extra assumption on my objects. Maybe I don't, okay, just thinking something that pops in my mind, like maybe you don't want to consider metric spaces, but only non-empty metric spaces or whatever, then you might want to build in this axiom early on, or maybe you realize, okay, I asked for non-emptiness, but I don't really need it, so a lot of my proofs simplify because I don't have to keep track of this stupid side condition of non-emptiness. And the point is that refactoring specs is easy, but refactoring a full library is a lot of work. And the same is true about papers. If you change definition 1 in your 50-page paper, and you have to like adapt the entire paper to this changed definition, that's a lot of work. So you maybe want to get the definition right before you commit to writing the full paper. And so you first write these specs and you work out the details later, and that's a perfect place where collaborators can join in, because sort of it's very clear from the outset which what spec we are really talking about at a given point in time and space. So formalization software agrees on what the spec is. If you're just talking at a blackboard about what you might want to be doing, then 3 days later someone might have forgotten some of the details. If you just look at the formalized code, it's absolutely clear everybody has the same thing in front of them, has the same thing in their hands. And again, when you're working with an extremely complex proof or extremely complex project, this reduces some complexity. So in the liquid tensor experiment, we used this a couple of times. I think the most prominent result of this approach was that we wrote down properties of Brindlein resolutions, which are some gadgets in homological algebra. And to prove that Brindlein resolutions exist, you need to deal with a whole lot of homotopy theory, basically up to finitely generatedness of homotopy groups of spheres. And it's a beautiful theory, but we weren't very excited about the idea that just to get the existence of these gadgets, we would have to formalize an entire book on homotopy theory. So we decided, well, we'll just write down the main properties and then claim that such an object exists, prove it by sorry, and then we would have one sorry in the entire project, but it would be extremely well localized, and people would say, yes, this statement is something that we know from the literature, we can trust it, etc. So we did that, and then we actually discovered an easier object with very similar behavior that basically fit in the spec. And that didn't require all this homotopy theory. So that meant that we could get rid of the final sorry, and that made us quite happy. So in general, key statements were written down without proofs and only by stubbing out definitions without really writing down the full definition. A very good example is that of the ext functors that show up in the main statement. I don't assume that you know what an ext group is, but it's something that takes a while to write down the full definition. But it has 2 or 3 main properties, namely, for the experts, if you plug in a short exact sequence, you get out a long exact sequence, and that kind of stuff. So we just wrote down those properties without being able to prove them because we hadn't even given the definition of ext. But we could work with this and continue working with that and accumulate the kind of properties that we really needed about ext, and then finally decide, okay, this is the correct order in which to prove them to minimize suffering. Okay, and so more importantly, several definitions and lemmas were tweaked along the way while figuring out what the correct specs were, or maybe while starting to fill in proofs of things that we were very confident about, we'd figure out, okay, but that spec doesn't actually really allow us to prove this. We need to tweak things a little bit. And Schulze says about this that actually this process of interacting with us while we were formalizing the work was what gave him a lot of confidence that we were actually working with the actual proof, because we discovered tiny mistakes the way you would expect in brand new mathematics of that complexity. And sometimes we really got stuck. And it wasn't just our naivety or stupidity that meant that we should have just seen, oh, well, you use that tiny result and you can continue, or you need to make this tiny tweak and then you continue. At some point, one statement really needed a pretty fundamental update. And actually some definitions had to be changed because, as stated, the result, well, was, I mean, again, in hindsight, you can see, okay, this is what was meant, but it was absolutely not clear how to tweak this from our point of view. So at some point, I think Schulze stayed up half of a night because he was really worried that we had found the point where everything broke down. But then the next morning he emerged and said, okay, here's a brand new proposition, prove this instead, and then let's see if we can continue. Right, and so what I sort of want to say is, you take this top-down approach, you write down your main statements that you're interested in, you stub out the definitions, and actually this goes against the common wisdom within formalization communities. They often say, no, you should take a bottom-up approach because otherwise you might not be able to make the ends meet. But we took this approach of saying, this is where we want to go, and now we're going to refine and refine and refine until we get to rock bottom. And that also meant that we could more and more distribute the work as it became more and more fine-grained. And well, I mean, sometimes large proofs or libraries actually did have to be refactored because we painted ourselves in a corner, and it was painful, as you might expect. But such is life. So next up is large collaborations and working at the interface of different fields. And I think this is, so far it has all been pretty technical maybe, but this is sort of something that we see happening in mathematics, and it might be happening more and more. I think 100 years ago, there were quite a lot of mathematicians who could claim that they understood all of the mathematics out there at that time, or certainly 200 years ago, there were a lot of people like that. But nowadays, I think there's nobody claiming to understand even 10% of what is out there. So we need to collaborate with people who understand parts of mathematics way better than we do. But so far, maths has been dominated by small collaborations. And Akshay mentioned this morning that actually it is increasing. We're seeing 10 author papers. We have these polymath projects that have been pushed by Tao and by Gowers. And technology is playing a role in this. So the talks, like the 5 talks that go on at the same time for 24 hours a day have been mentioned. But weblogs play a large role in polymath projects. I think the archive is a major influence in how technology is changing the face of mathematics, and Math Overflow as well. Yeah, so formalization software is one more tool in our toolkit, I would argue, and it easily scales to large collaborations. So we've seen a couple in the past. The Thompson theorem was formalized in Coq, so also known as the odd order theorem, with a team of about 15 contributors. And Tom Hales formalized this proof of the Kepler conjecture in the so-called FlySpec project, using the whole Light-Hole and Isabel theorem provers with a team of about 20 contributors. And like I said, in the liquid tensor experiment, we had a varying amount of contributors, but in total, it's about 15 contributors. So let me give a shout out to them. So I'll not read up all the names, but I want to give a special shout out to Adam Topaz, who really did an insane amount of work. And yeah, so we had a lot of fun together working on this all over the world, all around the clock. You would wake up the next morning and see, oh, people have been doing lots of stuff during the 8 hours that I was offline, and take off where they left. So we didn't just use Lean as a piece of technology in the liquid tensor experiment. We used some other components that I think were also crucial. So we took the lecture notes where Schultz had written his original proof, and we converted that to a LaTeX document with a bit more structure, using some extra LaTeX macros that created hyperlinks between the LaTeX version of the proof and the Lean version of the proof. And not just that, so in LaTeX we always refer to theorems and lemmas when we use them, of course. We never not refer to them, using LaTeX labels, but we never really explicitly with a hyperlink refer back to a definition when we use it. And so we actually did add that to this document, which allowed us to create automatically a dependency graph that tracks all the progress. And so this software that does this was not written specifically for the liquid tensor experiment. It was written by Patrick Massot, whom I mentioned in the beginning. He wrote that essay on why formalize mathematics. So he wrote this for his own project about sphere eversion and the Gromov-H principle, which he wants to formalize in Lean, and they're almost done. And so we reused that to create this dependency graph that allowed us to get a better view on what's going on in this proof. And then, of course, we relied on Lean as a proof checker to guarantee correctness and compatibility of all the different components. The result of this is that contributors can work on sub-projects that suit them without really needing to understand the full big picture. If they want to, of course, they can try to do this, but they don't need to. If they see, okay, here's this tiny bit of analysis with some tricky convergence proofs, but I like those kind of proofs, okay, they can work on those. And I will be very thankful because I have a background in algebraic geometry, and I forgot all the different ways of doing convergent proofs in analysis. And then you do have the assurance that everything fits together by this guarantee that the proof checker gives you. So let me briefly show what this looks like. So this is the online document generated from this LaTeX document. So it's an HTML website, but if we click on this, you'll see that it looks pretty much like a LaTeX document after we give it a few seconds to render. Right, so the remarks, definitions, propositions with proofs, and all the way at the end, let me scroll down to the bottom. Here we see this main statement that I posted in a slide at the beginning. And if you hover over here, then you get some little pop-ups. You can click on the Lean logo, and it will give you a hyperlink to the Lean code on GitHub. Let me increase the font size a bit. And well, you can see that this code is talking about X groups as well. But again, let me not really go into the details. So there are these hyperlinks, but as I said, we also have these graphs. And
what generated this text? Was it human generated or computer generated?
the LaTeX document was human written. We started from the LaTeX proof that Schultz had written, and then we refined that and adapted it. And yeah. So here's a graph. I see that. Let's see. Okay, now you should be able to see everything. So over here you have this node main theorem at the bottom. If I click on it, again, you'll see the main theorem that we're interested in. And this graph shows how all sorts of definitions and lemmas are pieced together to build up to the proof of this main theorem. So the way it works is boxes are definitions and ellipses are lemmas, propositions, theorems. Initially, everything was white. And then there's a legend over here which says, if something has a blue border, it means that the statement of this result is ready to be formalized because all the ingredients that are mentioned in the statement have been done. And if it has a blue background, then you can actually start working on the proof because all the ingredients needed for the proof have been done. And then gradually things became more and more green as we formalized more and more in Lean. And so this graph is, well, it isn't even that complex. And if this was the entire graph, then we probably wouldn't even have bothered. But so here there's this thing called first target, which doesn't have any, it's just sort of an axiom in this graph. Nothing contributes to its proof, but it's a really gnarly looking statement. And this was actually the statement that Schulze was worried about, like everything that goes into the proof of this statement, does that actually make sense, or did I mess up some inequality somewhere deep down in the proof? And so if we go back to the graph of section 1, then you can see that all the way down at the bottom, over here, there's first target, which is the exact same statement that was first target in the other graph. And this graph is quite a higher complexity, and it was extremely helpful for us to see what had been done, who's working on what is the next thing that can be done, how do things fit together. And this graph changed over time a lot, because when we started with the document that Schulze had written, the graph was actually simpler, but we discovered, okay, well, this proof actually makes quite a large jump. So let's add 2 helper lemmas to actually justify the proof, etc. And so it grew over time in complexity, but it really helped us to keep track of where we were going and how things fit together. Okay, and then right. So I think to summarize this part about collaborations and so how does it fit into the theme of abstraction boundaries? I think this graph is a new layer of abstraction boundary, where you're sort of saying, okay, these are the high-level components of the proof. These are the things that deserve to be called a lemma on paper or a proposition on paper. This graph had roughly 50 nodes, maybe 60 nodes. Of course, in Lean, there's 2 orders of magnitude more. Well, I would say let's say 20 times as much lemmas and definitions, etc. But there are all sorts of simple things that you wouldn't bother calling a lemma on paper. But this is sort of the high-level structure of the proof. And certainly when the proof is using different components from number theory, homological algebra, analysis, etc., it was very helpful for us to have these clear and precise specs where people from different fields could contribute, and we would be sure that everything would fit together and people would be able to confidently manipulate ingredients from parts of mathematics that they weren't very familiar with. So finally, communicating the results and how to give the casual observer some confidence that what we did is actually a proof of what Schulze had in mind. So this is what the statement looks like in Lean of the main theorem. And you'll see that there are similar ingredients. I already mentioned this X group. There was some curly M occurring in the statement, and a profinite set S, and a p-Banach space V, etc. So it looks very similar on some level, except that this is formatted in a monospace font, and the original thing was formatted using LaTeX. But, well, Ceci n'est pas une pipe, as Marguerite told us. So we could have done something very evil, or we could have done something very stupid. What if we had just defined X groups to be 0 to begin with? Because that's what the main statement is about, right? We need to prove that for all I, some X group is 0. Well, if we just define it to be 0, then we're done. Why spend 2 years working on this project? And who's going to check that we didn't actually do that? So there's a question there. And even if we're not evil, we could have done something stupid that would have completely trivialized the proof. So this is we're not the first people to think about this question. Pollack wrote a paper in 97 answering the question, how to believe a machine-checked proof. And he says, well, roughly on a high level, you need to trust 3 things. You need to trust the hardware on which you're running your proof checker. You need to trust the software, the actual proof checker itself. And you need to trust the formal statement. So is the statement actually saying what you think it is saying? And I claim that nowadays computer scientists have a pretty good grip on the first 2 issues. And it's worrying about these 2 is looking in the wrong place for errors. I think errors are magnitudes or orders of magnitude more likely to occur on this stage. So that's where we'll look. So how can a casual observer gain confidence that the following 3 things align, namely their mental model of mathematics and the pen and paper representation of mathematics that they might see in the literature, and some formally verified representation that they could see on some GitHub source code hosting thing? Well, if the statement is easy, something like Fermat's last theorem, which only mentions natural numbers, addition of natural numbers, multiplication, powers of natural numbers, the ordering of natural numbers, well, then you can just check all these definitions and check that they line up with what you have in mind. And maybe if you're slightly paranoid, you'd say, okay, I'll also check notation, because, well, there is this plus symbol, but does it actually refer back to the function that defined addition on the natural numbers, or does it just return 42 or 37 all the time? And then, of course, you'll never get equality. And if you're hyper paranoid, you might want to check for 0 with Unicode characters, because, well, you could insert some crazy invisible characters into this formal statement. Computers don't see the difference, and it might completely change the meaning. Well, but this is something that you could easily do for Fermat's last theorem. And with an hour of work, you could convince yourself that the statement is actually what is your mental model of the statement of Fermat's last theorem. And since you trust the proof checker, because that has been dealt with by computer scientists who really know what they're doing, and they didn't do it alone, etc., they have a very high confidence in a formally verified proof of Fermat's last theorem, which doesn't exist, by the way. But the main statement in the liquid tensor experiment, what we're dealing with today, relies on over 1,000 definitions. Because the main statement mentions real numbers, profinite sets, p-Banach spaces, condensed abelian groups, and these X groups, which are an example of derived functors. So that's a pretty finite list of definitions, but these gadgets are all defined in terms of other things. So recursively, all the way down to the bottom, there are like 5,000 definitions involved, I think. Well, and not only that, the main statement relies on some complicated notation to hide certain functions and parameters that are irrelevant in the sense that you would never write them down on paper. And we want the statement to match closely with what's written on paper. And finally, some intermediate statements rely on 0 with Unicode characters to automatically trigger some automation that we wanted to trigger without really messing up the readability of the statement. So maybe we did something evil. And I think there's no way that you can actually, if you haven't worked with Lean for 2 years on this project like I did, there's no way that you can justify investing half a year of your life to check all these definitions and notation and etc. to convince yourself that we didn't cheat. So I would suggest that people apply abductive reasoning. If it looks like a duck, if it swims like a duck, if it quacks like a duck, then it probably is a duck. But you shouldn't just say, well, the statement looks like the statement that Schulze wrote. So you should dig down 1 or 2 levels. And so what we did is we created an examples folder with 5 files that cover the 5 main ingredients in the statement. Like I said, they each focus on one object in the statement. And it was very important for us. We kept them short and well documented and readable, because as you saw, the statement of Euclid's theorem in Lean was really quite readable for anyone. Even if you've never seen Lean before, you can read that statement. The proof, however, was using these tactics like assume and have and use, and quickly becomes harder to understand. But the statements are readable, and that's important, and these files are short and well documented. And then they should exhibit the standard behavior of that object. And that should convince people, okay, this object satisfies the abstraction boundaries, the interfaces that I know about this object, and so I have a high level of confidence that it is doing the right thing. And so we have a blog post on our community blog that carefully documents all these examples and explains that a tiny amount of Lean syntax so that you know how to read these files. And it saves you reading 90,000 lines of code in the liquid tensor experiment, built on top of mathlib, which is 1 million lines of code of formalized mathematics by now. And this blog post is something you can read in 5 minutes. So here's an example from these example files. For example, the real numbers. You can implement the real numbers using Cauchy sequences or Dedekind cuts or whatever. It doesn't really matter. What really matters is the real numbers form a conditionally complete linearly ordered field. And, well, I didn't paste the proof because it doesn't fit on the slide, or at least then the other 2 examples wouldn't fit on the slide. But if you go to the examples folder, you will find an actual proof. And like I said, the proof doesn't really matter. What matters is that Lean agrees that the real numbers form a conditionally complete linearly ordered field. Whenever you have a conditionally complete linearly ordered field K, it is isomorphic to the reals, and this crazy symbol means, well, it's a bijection that preserves addition, multiplication, and the ordering. And whenever you have 2 of such isomorphisms, then they're actually equal. So it's really up to unique isomorphism determined by these properties. So the real number object in Lean behaves the way it should. And so you can do similar things for these X groups, showing that they preserve, turn long exact sequences, short exact sequences into long exact sequences. And I see that I went way further over time than I wanted to. I'm really sorry. So let me get to a conclusion. What we saw is that formal mathematics encourages abstractions by reducing cognitive load. I think this is one of the main points. It allowed us to understand a really complex proof, and it helps large collaborations. And yeah, so Akshay hypothesizes that our agreement on the validity of proofs is an important stabilizing factor in the social fabric of the mathematical community, causing an above average level of consensus. Can formalization strengthen our agreement on proofs, and hence increase the stabilizing factor, and hence increase our level of consensus? What we've seen today might be a rough first order approximation of Aleph 0, and I would love to see what a second order approximation looks like.